Good evening from the Jet Propulsion Laboratory in Pasadena, California, where for the past 2 weeks, American scientists have been giving the world some of the most staggering sights man has ever seen. It is the spectacle of the largest planet in our solar system, second only to the Sun in size and violence, a ball of roiling gases, 11 times bigger than the Earth. Jupiter has fascinated man since the astronomer Galileo, looking through a primitive telescope in the year 1610, noticed that the planet had moons. That discovery confirmed the theories of Copernicus and shattered the ancient belief that the universe revolved around our Earth, that man was the center of everything. 9 more moons have been counted since Galileo, making 13 in all, making Jupiter something like our own solar system in miniature. Studying it could reveal important facts about the origin of the universe and our Earth. This is a full-size model of the spacecraft Voyager 1, which passed close to Jupiter last week after a 16-month flight from Earth. It is now hurtling away from Jupiter towards the next largest planet, Saturn, where it will arrive in 1980. It has sent back more than 15,000 pictures, as well as information on radiation, magnetic fields, and other scientific data that will take years to analyze. But for laymen and scientists, the pictures are the most immediate and graspable part of this mission. Tonight we wanted to give you a closer look and hear some of the discoveries the scientists are still making from them. For instance, only today, they released the first color picture of perhaps the most startling discovery to date, that there are live volcanoes still erupting on Io, one of the moons closest to Jupiter. The pictures are received and evaluated here at the Jet Propulsion Laboratory, a facility managed for NASA by the California Institute of Technology. The nerve center for the $343 million project is Mission Control.
Yes, sir. Be advised from the Voyager subsystem teams, we have a go condition from the MCQ.
In this unglamorous office, all information from Voyager is first received, and the spacecraft is given its commands. From here, directions go out to the Deep Space Network, the one working area at the Jet Propulsion Lab that looks like a space-age operation. Here, scientists keep track of all our wandering spacecraft and correlate the monitoring from the various tracking stations around the Earth. The pictures come in as electronic pulses in digital code, 115,000 bits a second, and are translated by computer to black and white images, and finally to color. By combining images taken at intervals, they're able to simulate the movements of Jupiter and its swirling clouds. The Voyager mission, which includes a second spacecraft that will arrive at Jupiter in July, involves a team of 106 scientists from all over the country. The scientist in charge is Dr. Edward Stone of the California Institute of Technology. With him to go over the Jupiter pictures for us is Dr. Lawrence Soderblom of the U.S. Geological Survey, a member of the imaging team. Dr. Stone, I know the mission is incredibly complicated, but let's talk about one of your goals. It was to study the atmosphere around Jupiter, something we can actually see. Why is that important in relation to our Earth's atmosphere?
Well, we're certainly interested in what causes weather patterns here on Earth, winds, cloud formations, and so on. We have some ideas, some theories, which we use in the process of trying to understand such weather systems. We very much need to test those ideas, though, with another system, where, in fact, some of the factors that are involved in forming the weather are there in different proportions. If one looks at the Earth, which is 1/11th the size of Jupiter, perhaps the size is part of the difference. Another thing, of course, is that Jupiter has no solid surface, so in that sense can't support very large pressure differences in the atmosphere, so you cannot have such large high-pressure areas.
Now, what have we found so far? What have you found that has surprised you?
Yes, what has surprised us is that we had expected to see a great deal of flow along the bright latitudinal belts which one sees there in the zones. In fact, one can see in the movie that there are indeed wind patterns which are generally east to west and west to east, but we also see there's a great deal of turbulence, there are plumes, and the most surprising of all, there's a great deal of rotational motion.
I see. And why is that surprising?
Well, the theories which we had developed really should have resulted in more direct flow just of east-west and west-east flow. We expected the Great Red Spot to be basically to be a counterclockwise motion but we didn't really expect that there would be so many other areas with rotational motion. Here is, in fact, a film, a time-lapse movie of the Great Red Spot. One can see a cloud pattern essentially circulating about the Great Red Spot. It takes about 5 days and 19 hours for that cloud to completely circumnavigate the Great Red Spot.
Which is very large.
Which is very large. It's 3 Earths would fit inside the Great Red Spot.
Now, people have been looking at that Great Red Spot for hundreds of years, from Galileo onwards, now able to see it so close up in these incredible pictures. What have you learned about it that you didn't know?
Well, we have first of all learned that it indeed is a rotational, has rotational motion. We did not know that for sure. We very much want to see whether the material is in fact spiraling into the Great Red Spot or spiraling out from the Great Red Spot. That will tell us
which is it?
And we don't know that yet. We need to make very much more detailed measurements than we have been able to make to date. But we have the data.
What is this? This is another view.
This is another view which shows the blue, whitish blue area is the high altitude cloud, which in fact is circulating about the Great Red Spot. And the lower cloud deck you see here, which is red, presumably possibly because of red phosphorus, is a somewhat lower altitude and is somewhat warmer. We've measured its temperature.
What could that Great Red Spot be? What would be making it?
Well, one possibility is that it's an upwelling of material from deep inside the planet, and it brings up unusual amounts of chemicals and so on, and that there's a condensation of those chemicals once they reach the high altitude where it's cold, and that releases the heat. In a sense, it's a little bit like a tropical storm or a hurricane here on Earth.
Except that our hurricanes move around all over the place, and this one stays in one place.
That's right. This stays in one place. That's a puzzle which we were trying to understand. Another thing we're trying to understand is the composition of the atmosphere. We believe that Jupiter managed to retain a more representative sample of material out of which the entire solar system was made, though unlike the inner planets. Here is an image from Earth of infrared radiation, which is leaking out from the interior of the planet. Where the bright areas are is where the infrared radiation is coming out from deeper in the atmosphere. By comparing that with the Voyager image beside it, one can see that these clear areas tend to be between the bright white zones. Those clear areas are where we're going to study in detail the composition, chemical composition of the atmosphere.
I see. So, as far as the atmosphere is concerned, it's just raised more intriguing questions for you so far than given you answers from these startling pictures.
That's right.
There is also a white spot next to the red spot.
Yes, in fact, there are a number of white spots on the planet, and one can see now some hint of a spiral pattern in this cloud deck. Again, it's thought that this may well be a high-pressure region with material coming up from deep below, condensing into a white cloud, and then the spiral motion is associated with the outflow of the material from the center of the spot.
Now, another discovery we read about in our newspapers last week was you found a ring around Jupiter. We've always known there was one around Saturn, which we didn't know was there before. Now,
well, we had only some vague, inference from Pioneer 11 that there might have been one by looking at the trapped radiation measurements, but this is the first direct indication of the ring. This is an artist's sketch of the ring. We did not actually image the ring like this.
Now, what is the ring made of?
The ring is presumably very small particles of just rocky material, presumably. We don't know that yet. It's quite dark, and you can see the ring only when it's on edge. It's like a sheet of paper which is so thin that only by holding it up on edge can you get enough material to be able to see it.
What's this?
This is, in fact, the one image that we've taken. We opened the shutter on the camera, and since the spacecraft is a little bit, has a small nod to it, the stellar images, which are the small wiggles, basically are the multiple exposures as we kept the shutter open of essentially the star background.
I guess only you and your experts would know that was a ring, because I wouldn't guess that from that picture.
That's right. From edge on, basically what one saw was the diagonal shot of the ring, the diagonal image of the ring.
Now, perhaps the most dramatic thing about Jupiter are the moons, which we can see fabulously, a couple of them in this,
Io and
photograph
Europa
here.
are shown here.
Why are they so significant?
Well, they essentially are a miniature solar system in a way that Galileo could not have anticipated, and that is that the inner two Galilean satellites, Io and Europa, the two shown here, and you can see they're quite different in appearance, are dense rocky objects, much like our moon, and much like the inner planets. Mercury, Venus, Earth, and Mars are all dense rocky objects. While the outer two Galilean satellites, Ganymede and Callisto, are much lower density, presumably, as shown in this artist sketch, presumably the outer two satellites are maybe half water. And that's very, very similar to our outer planets. Jupiter, Saturn, Uranus, and Neptune, which have a great abundance of the lighter elements such as hydrogen.
So in other words, the outer little satellites of Jupiter are to Jupiter as Jupiter is to us.
That's
in other words,
right.
To the Sun.
That's correct.
And we are like these inner planets like Io, for instance.
Io and Europa, yes.
Well, to look a little further at the planets, let's turn to Dr. Soderblom, the geologist, who's an expert on the geology of these planets. Why is, let's take Io first, since it's the most
First of all,
dramatic one.
they're not little planets. They're planets of the scale of the inner planets of the solar system. We think of them as planetary objects.
As big as what, for instance?
As big, the inner two are the size of Earth's moon. The outer two are the size of Mercury. So they're planetary in scale. They just
Now,
happen to be orbiting Jupiter.
Io. This picture, I believe, shows the sodium cloud around
So
that
this-
was observed from Earth before
Right,
we
that's
got
right.
that close.
Using special telescopic instrumentation, scientists have discovered that there are sulfur, potassium, and sodium make up a ring around Io, which gives us some information about the surface chemistry.
Yeah.
So we expected Io to be somewhat unusual because of this cloud, which has in fact been photographed from Earth.
So we suspected also that it would be densely cratered, like the moon, because of its.
But it was not when
It
you.
was, well, as we flew in, this is the first image that we could see topography on the surface, and we thought we could see these dark rings to be impact craters.
That is actually Io swimming against the background
That's
of
right.
Jupiter's
Above
surface.
the surface of Jupiter. Jupiter is enormous, filling the screen, perhaps 100 times in total area. As we flew closer, we discovered that these things that look like impact craters, this thing with a white ring around it, donut, shows none of the attributes other than circularity of impact craters on the moon. And as we studied these more and more closely, we became more and more convinced that we were seeing something very youthful on the surface of Io, that the surface, in fact, did not show impact craters.
So it could be quite young compared to other parts of the solar system.
The surface could be quite young.
The surface, the body itself is probably 4.5 billion years old, the age of the solar system at large. But as we moved in, not only did we not see large impact craters, we couldn't even find the very small ones. And daily, our estimates of the youthfulness of the age of Io dropped and dropped, to the point that as we flew very close during encounter and started to see volcanic lava flows emanating from some of these dark spots on the
Show
surface.
us where you would see one of those. for instance.
These kinds of things. This is a...
We know that this is in fact a hot spot on the surface. This dark circular region with a light area inside looks a little bit like a lava lake, and we know that is hotter than the general surface of Io itself.
Here are a couple more. But as we flew close, I think we have a black and white showing that next volcanic center. There it is. We saw that there is, in fact, a collapsed caldera or pit surrounded by lava flows, which all the geologists immediately recognized as lava flows.
But you thought that had happened a long time ago. and
Well,
then
we
were
were then
startled
down
to discover that you really
That's
had
right.
some going now.
That's right. We had revised it down to less than 1 million years or so.
On Mars, this same area would have had 20 impact
Right,
craters
so
at
much
least.
older.
I see.
And then, lo and behold, the geysering of these current volcanics were discovered over the weekend, and since that time we've seen 6 or 7 of them active.
And this is one actually blowing
Right,
up.
blowing up, shooting material, both solid material and gas, the order of 100 kilometers above the surface of
60 miles.
Io, right? And they appear to be going off either continuously or at least several times in the few hours we were close to the planet.
Yeah. So what do you go away and think about when you go home at night as a
go away
result of
and think
having
about
found
the
that?
incredible. This is the most dynamic and active geologic surface in the entire solar system, far more active than the Earth.
Because we tend to think of all of things outside Earth being rather dead, don't we?
That's right. Well, we weren't very close in our prediction.
I see. Now, the next...
Europa is the next satellite out, and it is like the Moon again in terms of its being primarily rocky materials, but it does show surface ice. And in those that surface ice, the brightish material here, we can see crisscross patterns, which we really won't know what they are until July the 9th when Voyager 2 flies past. But we think
it's going to get a bit closer, is it?
They're enormous in scale. They cover, they're the order of 100 to 200 kilometers wide and thousands of kilometers in length.
So what's your hypothesis about
The
that?
hypothesis is that they're large fracture patterns of some type that in
In
which
the ice pack itself.
Or perhaps in the solid
perhaps
surface.
in the solid surface.
In the
underneath
solid
the
surface.
ice.
And the next
Next one is
Ganymede. Is the
Ganymede
next.
is the next one. Now this, again, is a larger body about the size of Mercury. And we saw, on approach to Ganymede, bright spots here and here, which we thought might be impact craters. As we flew closer, we could see the radiating patterns from them.
Presumably fresh ice, which has been
Been scarred. But as we flew closer, we also saw a series of very peculiar corridors and patterns on the surface, which we could very faintly start to see lines and ridges, as if a rake had been run through that corridor. And as we flew closer yet, we saw that, in fact, there were very complicated series of markings, and noticed that some of these corridors had been offset, and we could see the faults that had
lateral fault.
Well, what would
That's
that lead you to suppose?
It leads us to suspect that pieces of the crust of Ganymede have been broken and moved around past one another.
Like on the Earth?
Well, it's not to be likened directly to the plate tectonics, but it's what might happen if the same driving mechanism were moving things around on the Earth, but ice and water were involved rather than molten rock and rocky crust. In other words, the ice tends to float, whereas solid rock tends to sink. So this is analogous. This is the first place in the solar system we've seen major lateral tectonics.
Plate motion.
I see. And finally, Callistus.
Callisto, again,
Callisto, I'm sorry.
an icy body suspected to be roughly 50% water. And as we flew in, we saw a myriad of bright spots, impact craters, some fading into the background, some younger ones.
You say as we flew in, you actually felt, did
Well,
you?
yes.
You were getting there
I had
yourselves?
difficulty in not believing I was in the pilot's seat, but as we flew very close, we started to see an immense circular structure looking somewhat like what you'd get if you sliced an onion in half. This thing is the largest contiguous feature in the solar system, and our model for it now is to imagine dropping an enormous brick 5 kilometers on a side into a frozen ocean. And what would happen is it would penetrate the crust, the ice, and send out ripples, much like dropping a pebble into a pond. These ripples then may have fractured the crust and allowed water to erupt, leaving this record. But no other record of that enormous
But this is an
event.
ancient surface. It's full of
That's right.
craters. It's probably 4 billion years old. It is the oldest surface of those that we've seen on the Galilean
Now,
satellite.
why with 13 moons around Jupiter would there be some of them so very old and some of them with very young surfaces? Why? What possible explanation could there be for that?
Because what goes on, how a planet behaves, what lifeline it goes down, depends very much on its initial makeup, its chemistry. How much heat did it get when it was originally put together? How much heat did it get from the radioisotopes or the radioactive elements inside? It's the basic question we're trying to understand is what happens to a planet, any planet? Why does it go down a particular lifeline? And it's these kinds of factors, the chemistry, the energy. And so we're looking at the Earth now as not by itself, but it's only one member of a suite of 9 or 10 things.
Now, this picture that's come up now reminds me that the other startling discovery that you've made so far is that there are or may be lightning bolts on Jupiter. Dr. Stone, what's the significance of that?
Well, first of all, let me explain the picture. This is an image taken of the dark side of Jupiter. If there were no light at all, one would have expected a dark image. First of all,
Is that the light from our sun showing around the rim
that
there?
is the straight, more or less curved, somewhat curved line is essentially an auroral arc or a northern light display on the horizon of Jupiter. And so we have photographed an auroral light display, which we had already discovered in the ultraviolet, by the way, on our way into Jupiter. The bright points which you see down somewhat lower in the image are in fact thought to be best explained as though they're thunderbolts or essentially lightning bolts above the cloud deck.
Now, what would that, why would you get excited about that?
Well,
Is there lightning anywhere else in our universe? that
Well,
you know
certainly we
about?
have lightning here on Earth, and now we think that there's also lightning on Venus. Once you have lightning and arc discharges, it's possible to essentially do some chemical processing, which would tend to lead to the buildup of larger molecules.
Yeah, because one theory is that life could have started on Earth by electrical discharges fusing together primitive substances to form compounds which eventually became life. Is it conceivable that could be happening?
I think it's quite unlikely in the case of Jupiter. First of all, there's no solid surface for the material to essentially reside on. It's being processed up at an altitude where the temperature is about minus 230 degrees Fahrenheit below zero.
That would be very cold life if there were
Yes, very
any.
cold life.
Well, now, Voyager leaving Jupiter is going on to Saturn, where it reaches in about early 1980, I believe.
November 1980.
November 1980. Is it at all likely that there would be a climate any more hospitable there to life? Do you have any serious expectation of finding any there?
I don't really expect that we'll find life, but we certainly have an object called Titan, which is a large satellite of Saturn, which has a solid surface and has an atmosphere. So it's certainly an object where, in fact, some chemical processing should or most likely has gone on.
Let me ask each of you, you, Dr. Soderblom, first. Of all the things, the sort of amazing shocks to your scientific psyche you've had in the last couple of weeks, which is most important to you?
Oh, I think the discovery of active volcanoes on Io has to rank well above all the rest. To find a surface this incredibly active in the solar system, more active than the surface of the Earth stretches the imagination beyond its limits.
Where does it stretch it?
It stretches it in the sense of, again, adding a new concept or changing our philosophy about what are the incredible breadth of directions that a single planet could follow. This is perhaps the end member of the most active.
And Dr. Stone, what would you...
Well, I think I would agree that the volcanism is, in fact, the keystone, not just because of the interest it has with respect to the evolution of planetary objects, but because the volcanism also is undoubtedly affecting the entire environment of Jupiter. It is injecting, essentially, these gas clouds into the magnetic field. The torus or donuts of ionized sulfur, which we observed on Orion, are all related, if you like, we think, to this very important object called Io and its volcanism.
Well, thank you both very much for sharing these marvelous pictures with us today and talking about them. There are a couple of things worth mentioning in conclusion. Today happens to be the 100th anniversary of the birth of Albert Einstein, whose theories on the nature of time, space, and energy helped to make this kind of space exploration possible. It's also interesting and a little scary to note that once this spacecraft is finished with Saturn, it will go off on another journey. The first time man has attempted to penetrate outer space. It will take Voyager some 40,000 years to reach the nearest star. And just in case it's found by some beings of advanced technology, it carries this gold plate with symbols instructing them to play a recording inside. And that carries messages and pictures from Earth. But for the years it will take Voyager to get there, scientists will be continuing to study the flood of information Voyager has given them on Jupiter. That's all from us tonight. We'll be back tomorrow night. I'm Robert McNeil. Good night from Pasadena, California.